Chemistry, we continue our study of the atom. This is Lesson 9, Discovering the Atom. So in 1913, Danish physicist Niels Bohr proposed the theory that electrons travel around the nucleus in fixed orbitals. They don't just fly around freely. An orbital, also called a shell, has an energy level at which electrons must stay. Electrons can pass from one orbital to another, but they cannot stay in between orbitals. Niels Bohr came up with the idea of circular orbitals. You will learn later that the shape of the orbitals is more complex than this. So electrons in orbitals further from the nucleus have more energy. The nucleus is pulling them in, and as they gain energy, they can jump up to higher and higher orbitals or energy levels. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. In 1897, English physicist J.J. Thomson discovered the electron. Thomson placed a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. By placing a magnet on the side of the tube, he caused the electrons to curve. He was able to determine the mass and charge of an electron. So it's kind of like a machine gun firing electrons. So they're going from the left side over to the right side. The left side is negative, so it's repelling the negatively charged electrons, and it's flying across that tube and going over to the positive side. And that's attracting the electrons. And then you can see in the picture down below, and that's actually a picture, that's not just an illustration. So you're actually seeing a stream of electrons, that white line there in the middle. And by putting a magnet to that, you can cause them to either curve toward the magnet or away from the magnet, depending on which end of the magnet you're using. And by doing that, he was able to determine how much charge they had and what their mass was. So a negatively charged plate is called a cathode, repels the electrons. A positively charged plate, called an anode, attracts the electrons. This creates a visible stream of electrons in gas. And a magnet causes the negative electrons to change directions. In 1904, Thomson proposed a model of the atom that included electrons. He knew that there must be positive charge to balance the negative charge of the electron. He believed that the positive charge was evenly distributed in a sphere with the electrons spread around the sphere. So that's the model that he had. That large pink circle is the sphere. It's uniformly has a positive charge because back then, scientists knew that you had to have a balance of positive and negative charge. And so he thought it was just spread throughout that big pink ball. And so the electrons were these little objects placed inside of that pink ball, these little negatively charged objects. This became known as the Plum pudding model of the atom because it was a soft, solid sphere with chunks of electrons. So he was English, Thomson was English, and they have this stuff in England called pudding. It's not like what we think of pudding. It's more like a kind of a cake or a bread, but it has spices in it and it has different things stuck in it. So there you see a picture of plum pudding there, and so they called it the Plum pudding model of the atom. In 1911, Ernest Rutherford performed his gold foil experiment. The experiment demonstrated two things. One, that an atom has a solid nucleus center, but that most of the atom is empty space. So this refuted Thomson's theory that the atom was a big, uniformly charged positive blob with a bunch of little electrons stuck in. Instead, Rutherford came up with the idea that all of the positive charge was in this solid nucleus in the center, but that the electrons flew around outside of that, and that most of the atom is actually empty space. So most of your body, 99.99% of your body, is empty space. So Rutherford shot alpha particles, and we'll talk about what those are later. They're positively charged particles at a thin sheet of gold foil. If Thomson had been correct, the alpha particles would have shown a small deflection. They would have either gone through these pink blobs that he thought were just soft positive charges, or they might have deflected a little. The positive charge might have deflected these positively charged alpha particles and caused them to maybe curve a little bit. In fact, most showed no deflection, and some actually bounced back. This indicated a solid nucleus surrounded by empty space. In fact, Rutherford was so shocked by this, he said it was as though you shot a bullet at a piece of tissue paper and that it bounced back at you. That's how surprised he was to see any of these particles bounce straight back. So that's what indicated to him that there must be something very solid inside the atom, a very solid center to it. So here's just an illustration. So these little red dots are alpha particles, and most of them miss the nucleus. Again, most of the atom is empty space, so they'll just fly straight through from left to right. You see most of them doing that. So most alpha particles miss the nucleus. Some are deflected. They get close to the nucleus. The nucleus has protons in it. That's positive charges. And the positively charged alpha particles will get close to that. They'll be repelled by the positive nucleus and get pushed away, and they'll curve. A few hit it directly, however, hit the nucleus directly and bounce back. The discovery of the proton is credited to Ernest Rutherford, who proved that the nucleus of a hydrogen atom, i.e. a proton, is present in the nuclei of all other atoms, and he did that in the year 1917. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton, but no electrical charge. This particle was called a neutron. So the three parts of an atom, which you learned probably as early as middle school, protons, neutrons, electrons, they weren't even discovered until about 100 years ago. The last of those, the neutron, was discovered less than 100 years ago. So it's been a very short amount of time in the grand scheme of human history that we've understood what an atom is and what it consists of. So protons and neutrons each weigh about 1,820 times more than an electron. So if you put the nucleus of a helium atom floating above the middle of San Diego Stadium, which no longer exists, but when it did exist, I use this example, and the stadium were the atom, the nucleus would be about 1 millimeter in diameter. So the electrons would be in the upper level. So most of the volume of the atom is empty space. So there you see the nucleus of, say, a helium atom. It's 2 protons, 2 neutrons. We'll talk about that later. But it would be so tiny you wouldn't even see it. It would only be 1 millimeter, one of those tiny little lines on a meter stick. And it would be right there in the middle of the stadium. So the electrons would be way up in the upper deck outside there, and they would be even tinier than that. They would be invisible. They would be so small. So that's how much of an atom, relatively speaking, is empty space. It's all that area in between the nucleus and the electrons. An isotope is an atom of the same element, but with a different number of neutrons. So remember, neutrons have no charge, so it doesn't change the charge on the atom. So this is a lithium atom, and it has 4 neutrons, 3 protons, 3 electrons, and then 4 neutrons. So that's a lithium-7 atom because it has 7 what are called nucleons. I don't use that term a lot, but nucleon is the general name for either a proton or a neutron. They're called nucleons. So it has 7 nucleons, 7 protons or neutrons. There's a lithium-6 atom. It has 3 neutrons, so it has 3 protons and 3 neutrons. A lithium atom must have 3 protons. That's what defines it as lithium. Remember, in an earlier lesson we said that what defines an element's identity is the number of protons, not the number of neutrons, not the number of electrons. So lithium must have 3 protons. So both of those atoms have 3 protons. It's just that one of them has 4 neutrons, one of them has 3 neutrons. So the lithium-7 is a little bit heavier than the lithium-6, but it has the same charge, and it's still lithium. So here's the notation for an isotope. So if you look at the one on the left, lithium, it has the Li, the symbol for lithium that you'll see on the periodic table. We'll go over the periodic table shortly. And the number down below is the number of protons. That identifies it as lithium, 3 protons. The number at the top is the total number of nucleons, the total number of protons and neutrons. So that's the 7. If you look at the one on the right, it has to have 3 protons to be lithium, but it only has 3 neutrons, so 3 protons, 3 neutrons is a total of 6. Generally, this notation is used only when we deal in nuclear chemistry, not so much in conventional chemistry, so you won't see this notation used a whole lot. It's only important when the number of particles, the number of nucleons in the nucleus is important, and usually that's in nuclear chemistry, not in conventional chemistry that we talk about in this class. So the mass number, the mass of a specific isotope is on top and the atomic number on the bottom. So that is called the mass number on top. We'll talk about how it arrives at that for mass. So that's basically the weight. So an alternate notation that you saw earlier is Li7 for the lithium with 7 nucleons and Li6 for the lithium with 6 nucleons. That is 3 protons, 3 neutrons. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number. An ion is an element of an atom that has a different number of electrons than protons. So that's going to affect the charge. Ions are much more important in chemistry than isotopes because they have different charges on them. They have different numbers of positives than negatives, and that affects their properties in chemical reactions. So you see again a lithium atom on the left, and that's an electrically neutral lithium atom. So electrically neutral means it has 3 protons, 3 plus charges, and 3 electrons. That's 3 minus charges. 3 and 3 balance each other, and so the term for that is electrically neutral. So the lithium atom on the left has 3 protons and 3 electrons. Neutrons have nothing to do with whether something is an ion or not. They're not relevant to that. That has to do with isotopes, but neutrons are not important. So the lithium atom on the left has 3 protons and 3 electrons, so the charge is balanced and the atom is said to be electrically neutral. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. Because it has one more plus sign than minus sign, that means it's a positively charged ion. And the removal of that extra electron, we'll talk about why and how that happens. That's called ionization. It's making an atom into an ion, ionization. An anion is an atom that has more electrons than protons. So what you're looking at here is a fluorine, it's a fluoride ion. So this fluorine atom is an example of an anion, and once it becomes an anion, it's called fluoride. We'll get into naming in about a week. It has one more electron than proton, so count that. It has 9 protons, those are the plus signs inside the nucleus, and it has 10 electrons, 2 in the first orbital and then 8 in the second. That's a total of 10. So it has one more electron than proton, so that gives it a negative charge. So the little mnemonic or memory device is that this grumpy guy is a negative antion. So just remember, anions are negative. They're not called antions or anions, but they're negative. Okay, so they have a negative charge because they have more electrons than protons. A cation is an atom that has more protons than electrons, so in the other direction. So the lithium that we looked at on the previous slide is an example of a cation. It has 3 protons, 3 plus signs, and 2 electrons, 2 minus signs, which gives it a positive charge. So this dude is a positive cation. So cations are positive ions, anions are negative ions. The atomic mass of each proton and each neutron is 1 atomic mass unit. That's just the definition of an atomic mass unit. An element's rounded atomic mass number tells how many total protons and neutrons one atom of its most common isotope has. So 1 proton is 1 atomic mass unit, abbreviated AMU. And 1 neutron is 1 atomic mass unit, abbreviated AMU. So for the purposes of this class, we say that they weigh the same. A proton and a neutron weighs the same. Technically they don't. A neutron's a little bit heavier than a proton, but for the purpose of this class, unless stated otherwise, we just assume they have exactly the same weight, same mass, and that is 1 atomic mass unit. So an atomic mass unit is the mass of a single proton or the mass of a single neutron. The technical definition of an AMU is that it is equal to 1/12 the mass of a carbon-12 atom. The mass of a standard carbon atom was 6 protons and 6 neutrons. We're never going to get into that definition. That's just the technical definition. I'm just stating it for you here. But for our purposes, an atomic mass unit is the mass of a single proton or the mass of a single neutron, which we're going to take to be the same. An AMU gives scientists a unit of measure for mass on the atomic scale. However, the atomic scale is not practical. We can't weigh an atomic mass unit on a scale. Okay, and that takes care of this lesson, learning a little bit more about atoms, specifically isotopes and ions. In particular, you'll be hearing the word ion very frequently in the class. It's an important part of chemical reactions and chemical bonding.